This slide will help us review the density of a gas a little bit. Here it's asking us to arrange the following gases in order of increasing density at STP. And so we've got 4 different gases here. We have neon and chlorine and fluorine and oxygen. Neon is a noble gas. It is not a diatomic element, but chlorine, fluorine, and oxygen are all diatomic elements, so that when you have the gas, the formula is Cl2, and that makes a big difference. So this kind of problem is pretty common on chemistry exams, where it asks you to order something, put them in order. And it can be confusing to students, so I'm going to explain the problem. So in order of increasing density, that means you start with the smallest thing, and as you go through the list, it increases. It gets bigger. Sometimes they'll say decreasing, right? And then you start with the biggest and go to the smallest. And then greater than, less than signs can also be confusing. One end of this is pointy and small, and one end is like big, like a mouth, right? So the big end goes to the bigger thing, and the small pointy end goes to the smaller thing, okay? So how can we identify relative densities of these gases? What's going to affect the density? The grams.
There were so many answers given.
There's part of the answer I'm looking for. I couldn't quite hear what you were saying.
I said temperature, but maybe I should not say that.
We'll pretend you didn't. So this is at STP.
Oh.
So the density is grams per milliliters or grams per liter, but how can we figure out which one of these is more dense or less dense? The molar mass, right? So weird thing about gases, if you have equal volumes of gases, they have equal moles of particles. Doesn't work with solids or liquids, but it works with gases. So here, if we had a liter of each of these gases at STP, they would each occupy 22.4 liters. So their volumes would be the same. But would their masses be the same? No, because 1 mole of neon does not weigh the same as 1 mole of fluorine. So what we're looking for here is the trend in molar masses. And if they were all monatomic, we could just look at the periodic table and do it, but since there's a 2 in most of them, let's see, neon is, and we can be approximate here, neon's about 20, and chlorine is 35 times 2, so about 70. Fluorine is 19 times 2, so that's 38. And oxygen is 16 times 2, so that's 32. So equal volumes, equal number of moles of gases, but which one is going to weigh the least? The neon. So that means that neon is going to be the least dense. And what I would encourage you to do if you're doing a multiple choice question like this, before you go looking at all of those, just put them in order yourself, write it down, and then find the one that matches. Otherwise, it gets really confusing. So this is the smallest one. What's next? Oxygen. Yeah, just, there's no trick to this right now. Okay, so what's after oxygen? Fluorine. And then what's last? Chlorine. This is going to be the heaviest. That's going to be the lightest. So we got these in order, and now we look and see which one is the same, and that would be A. Any questions? Molar mass of a gas. We can calculate the molar mass of a gas or the molar mass of a volatile liquid. Volatile means that it evaporates easily. So what we can do with the volatile liquid is that we can weigh a sample of it, so we'll get the mass, and then we'll heat it until it becomes a gas. When it's in the gas state, we can measure the temperature of the gas, the pressure of the gas, and its volume. And then we can figure out how many moles there are using the ideal gas law. So molar mass is the mass divided by the moles. So from weighing the sample, we get the mass, and using the ideal gas law, we calculate the moles. Let's do an example. So a sample of a gas has a mass of 827 milligrams. Its volume is 0.27 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. So always good to go through and identify the values that you've been given. You get that one and this one and here, lots of things. And then see what do we want to find? We want to find the molar mass. So if you're finding the molar mass or you're finding the density, you're going to use an equation. So molar mass is equal to the mass in grams divided by the number of moles in that sample. Well, do we have the mass?
Yes.
Yeah, we do. It's in milligrams, but they gave us the mass, right? So the mass of this gas is 827 milligrams. We need it to be in grams. And so a very fast way to convert that is to say, well, that's 827 times 10 to the minus 3 grams. Not proper scientific notation. Your calculator doesn't care, and neither do I. So that's this part. How do we find the moles of gas? Ideal gas law. So we know that PV equals nRT. And we need to solve this equation for N. So divide both sides by RT. The R's cancel out, the T's cancel out on this side. And we end up with N is equal to the pressure times the volume divided by R and T. If you have any trouble rearranging this equation, please come talk to me and we'll get it figured out, because it's kind of important to know how to do that. So we are given a pressure. It says the pressure is 975 millimeters of mercury. Is that a good unit for the ideal gas law? No, it's not. We need atmospheres, right? Because R is 0.08206 liters times atmospheres divided by moles times Kelvin. So these are the units we have to have on the other things. So we need to convert that to atmospheres. So we're going to convert millimeters of mercury to atmospheres. So we want to multiply by atmospheres and divide by millimeters of mercury. You put the units in first. And then there's less thinking. The units tell you where to put the numbers. 1 atmosphere is the same as 760 millimeters of mercury. I don't know why I put that over there. Let's get it out of the way. I got 6 calculators up here. So we should be set. If one is being disagreeable, I'll just switch to another one. Yeah, they're all lined up there. 1.28. This should have 3 sig figs, 29 atmospheres. So that's the pressure, and they gave us the volume, right? Volume equals 0.270 liters. Is that a good unit? Yeah. And the temperature is 88 degrees Celsius. Is that good? No. Let's convert that to Kelvin. So 88 plus 273 is 361 Kelvin. Okay, so now we can calculate the moles. The number of moles is equal to the pressure, 1.2829 atmospheres, times the volume, 0.270 liters, divided by R, 0.08206 liter atmospheres per mole Kelvin, so many units, and the pressure. Not the pressure, the temperature. You knew what I meant. So getting to this point is one thing. Getting your calculator to give you the correct answer for that is another thing, because there's often a miscommunication when you talk to your calculator. Because you're thinking, well, it's this number times this number divided by this number times this number. But your calculator is then going to end up giving you, well, let's do it with letters because it's faster. If I do on my calculator A times B divided by C times D, the calculator gives me A times B divided by C times D. That's not at all the same number, especially when that number is a big number, like 300 something, right? So when I do this on my calculator, I do this times this, divided by that. If that works for you, great. Most students, that doesn't help. So what you should do is use parentheses down here when you're going to multiply them. So this times this, divided by, open parentheses, that times this, close the parentheses. And then you'll be speaking the calculator's language, and they'll give you the right answer. So get out your calculator and make sure it's behaving itself. Last night, it was me that kept making the mistakes. So if I get something wrong, please yell it out. Oh, that's wrong. What did I do? No. I did the thing I was just telling you not to do. So if you get like 1,500, you didn't use your parentheses correctly. So I'm getting 0.01163 moles. Again, we've got 3 sig figs here, and 3 down there, and 3 over here. So this should have 3. It seems like a small number, doesn't it? But we have less than a liter of gas. At STP, 1 mole of gas would be 22 liters. So this is not at STP, but it's not terribly far from that. So if we've got less than a liter, we're expecting much less than a mole of gas. So now we can calculate the molar mass. The molar mass is equal to the mass in grams, 827 times 10 to the minus third, divided by the number of moles, 0.11693 moles. What did I do wrong? You see it? I forgot the 0. It's 0.011693. So 70.7 grams per mole. Is that a reasonable molar mass? Like, I don't know. What's unreasonable? What if I got 0.5? Can anything have a molar mass of 0.5? What's the smallest element? Hydrogen. It's got 1 proton. There's no smaller one that we haven't discovered yet, right? 1 atom of helium has a molar mass, single atom, not the molecule, of 1 gram per mole. So we can't get smaller than 1. And then if you end up with something like 1,500 or, some really, really big number, that's probably not reasonable for this class. Any questions? Here's another example. This is similar to an experiment that we're going to be doing, experiment 6A. So an organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and reweighs it. Her data is given below. Calculate the molar mass of the liquid. So let's just talk about this real quick. So we're going to use an Erlenmeyer flask. It doesn't specify what kind of flask. It's a colorless liquid, which is really hard to draw. I'm going to make it purple. Okay. She puts some liquid in the bottom, and then she sticks this in a hot water bath. It's bubbling, right? Boiling. That's going to heat the flask and what's inside. And as this volatile liquid, which evaporates easily, begins to evaporate, it will get into the gas state and begin to fill the flask up. It also pushes the air that was in there out. So it goes into the gas state. Maybe we could do it like this. And now it's filling the flask. And it's actually coming out. So we heat it until you can't see any liquid left. It's all been converted to a gas. And then you close the flask and take it out of the boiling water. So you measure the temperature of the water. That is going to be equal, presumably, to the temperature in the flask, because it was in the boiling water, right? This container was open to the atmosphere, so the pressure in the container is the same as the atmospheric pressure outside, which you can read with a barometer. So that's where they get this pressure. And then you can determine the volume of this container. We need the volume all the way to the top. There's a couple of different ways you can determine that. But here the volume has been determined. It is 213 milliliters. So we have the volume and the temperature and the pressure of the gas. We can calculate the moles. Any questions about this? So again, the units aren't right. And they're not doing that just to mess with you or make your life hard. You know, when we do this experiment in the lab, we're going to measure the volume in milliliters because that's the appropriate unit. And we'll actually measure the, well, today it's on millimeters of mercury. So today it's 762.5. But it might be set on inches that day. Who knows? Are these units good for the ideal gas law? No. So the 213 milliliters, you need to convert that to liters. So 213 times 10 to the minus 3 liters. Again, I'm just writing times 10 to the minus 3 instead of milli because that's what it stands for. If you can do it in your head where you're like, oh, well, I need to move the decimal 3 places, it's 0.213, awesome, you can do that. But if you're one of the people that tells me it's 213,000 liters, don't do it like that. That's like telling me that an inch is equal to 12 feet, right? We know that's ridiculous because we know how big an inch and a foot are. Milliliters and liters, somehow your common sense doesn't apply to that. So we want to avoid that. 100 degrees Celsius, need that in Kelvin. Here the temperature was measured. The temperature was measured more precisely. We actually have 1 decimal place. So then we really should use the whole 273.15, 373.15 Kelvin. And the torr, we're going to have to convert that. We want atmospheres, and we want to divide by torr. .99211 atmospheres. So let's find the moles. We rearranged the equation in the previous slide, so we're not going to go over that again. N was equal to PV over RT. So we're going to take our pressure, 0.99211 atmospheres, multiply by our volume, 213 times 10 to the minus 3 liters, divide it by 0.08206 liter atmospheres per mole Kelvin, times the temperature, 373.15 Kelvin. As is typical with examples in the book, we've got 3 sig figs limiting. So do this on your calculator. 0.99211 times 213 EE minus 3 divided by parentheses 0.08206 times 373.15, close the parentheses, equals. Did you get that number? If you get a big number, you're accidentally multiplying by the 373 instead of dividing by it. It makes a really big difference. So, molar mass is equal to the mass in grams divided by the moles. So we just found the moles. Did that car alarm finally go off? How do we find the mass? We're going to have to subtract. So this is the flask and the gas. So we want just the gas, so we need to subtract the flask. So it's kind of stacked up for us over there. So 78.416 minus 77.834 0.582 grams. So 0.582 grams and 0.00690011 moles. So we get a molar mass of 84.3 grams per mole. That's a reasonable mass. Any questions?